Thanks everybody for coming along and to this session on sustainable seas. And we've had a couple of talks or several talks dealing with values and how to involve people in science and participatory processes. And I want to talk a little bit today about some of the biophysical science that we're conducting within the challenge, and hopefully towards the end how that's going to feed back into some of the other elements of the challenge that you've heard about today. So before I start, I'd just like to acknowledge all the other researchers that are involved in this program and within the Tipping Points project. One of the really nice things about the challenge is it's allowed us to bring together expertise across many different institutions, and that's been a real pleasure to have, being able to work with this great bunch of people. And it's also driven a lot by the postdocs and the students who are also involved in this program as well. So I'd just like to acknowledge their input so far. And of course Simon Thrush, who's currently in Antarctica, who pulled all this together and would have been here today if he wasn't cold somewhere else. So if we have a little think about the coastal environment, it means many, many different things to different people. And no matter what part of New Zealand you're from, you're probably interacting with the coast. And this coast is probably the most contested and multi-use space that we have in Aotearoa. And a lot of the goods and services that we obtain from this coast, leisure, recreation, food provision, cultural and spiritual values, is all underpinned by hidden infrastructure that we don't really think about or interact with very much. And that hidden infrastructure is the interactions that occur between the animals and the plants and their environment. Now those interactions are really, really complex, often non-linear. They operate over multiple different spatial and temporal scales. So if we take, for example, the shellfish that exist in our estuaries and harbours, when in high densities, the filtration capacity or the ability to keep the water clear means that will sustain aquatic vegetation. That aquatic vegetation may be habitat for juvenile fish that ultimately provides food provision in offshore waters. So it's those hidden interactions, that hidden infrastructure that maintains all these goods and services that as a society and a culture we enjoy about our coastal environments. Now this hidden infrastructure is under threat and can be impacted by the activities we have in the marine environment, and particularly in the coastal environment, often the activities that are occurring on land. Now these stresses that are occurring in the environment can be point source stresses, such as we had in the case when the Rena went down in an isolated case, but more often than not they're occurring over multiple scales and often cumulative in their effects. That means they accumulate through time and through space. So some of these stresses we may not think of, such as the increasing sedimentation into our coastal waters. You can see the effects of rainstorms at the spatial scale that occurs within the Cook Strait, Taranaki Bight, Tasman Gold Bait in that picture there. So these stresses are occurring locally. They can occur and we may have some control over them, but also we need to put that in a broader scale context and think about other stresses that are interacting with our hidden infrastructure that may impact upon it. That includes such things as climate change. We're in a warming world, and increasingly, due to increasing atmospheric CO2, a more acidified oceanic world. So these stresses aren't occurring in isolation. They're interacting with each other and impacting upon the system which we derive these goods and benefits from. Now it may seem that the system's absorbing and has the capacity to carry on as normal in the face of these increasing stresses. Now that occurs because of the positive feedbacks between the organisms that are interacting with the environment allows them to maintain themselves in a certain state. But as we push this system, as we nudge it along, as we increase our activities in the catchment, as we increase the intensification of fishing or harvesting in our coastal waters, the system becomes vulnerable to change. Now the point is we don't necessarily see that change coming. And so a relatively small change in stressor can have catastrophic effects. It's illustrated quite nicely in this little diagram here with the goldfish leaving this small pond to this rather big pond. And that can generate surprise. That can generate big changes in how the system functions and how the system is wired, and consequently the delivery of those goods and services to humanity, that loss of those cultural and spiritual values as the system changes. Now these sudden changes in the system, even though there's no direct stressor or direct increase what we can perceive as increasing the amount of stress on the system, is known as a tipping point. And it's a consequence of how these systems are wired. All these complex interactions that are going on between the plants and the animals and the environment that maintain those goods and services make them vulnerable to these rapid state changes. And so, sorry, I just need to go back a bit. So this is the science of tipping points. And often we can only view a tipping point in hindsight. When we look back up to see what we've lost, then we realise what the causes were. Now, the important thing about these tipping points is once you've passed one, it's a fundamental shift in how the system's wired. Everything changes. And it's very, very difficult to shift that system back into the state that it was in previously. Because all the things that maintained it in a good way for a long period of time have been reorganised and re-altered, and that system, that new state, has a hysteresis that makes it very difficult to change. Perhaps one of the best examples of a system going through a series of tipping points is what's occurred in Chesapeake Bay. So that's a large estuary on the east coast of the States, effectively where Washington DC drains into that. And this has gone through several tipping points or several major rewiring of the ecosystem through time. If we go back to the 16 and 1700s, it was a system dominated by fish, birds, and basically the indigenous people of the area. As the system became populated, as farming increased, it went through a major shift, and it was a system dominated by oysters, rockfish, submerged aquatic vegetation, seagrasses, towns and farms. Currently, with the overfishing of the oysters that occurred in the early 1900s, it shifted again into a system dominated by crabs, herring, and cities and suburbs. And it's probably vulnerable to a final tipping point where it's dominated by algal blooms, jellyfish, and very, very large cities. At each of these stages, there's been a major shift in how the system functions and also the goods and services that humanity derives from them. So from a management perspective, we need to be very, very concerned about these tipping points because they represent major changes that we don't necessarily see coming. Many of you and sitting in this room will observe changes over our lifetime within New Zealand coastal waters. So a nice photograph here of mussel or atrina beds in the Maharangi Harbour in the late 90s taken by Simon Thrush. A revisit to that site almost 20 years later, a completely different landscape. All these points on the right-hand side of the slide will be things people are familiar with. Loss of seagrass, reduction in numbers of shellfish in harbours, changes in fisheries, what we're catching, the size of what we're catching, loss of habitat structure, sediment impacts, and increasing nutrient levels. So all of these are indicators of increasing stress within our coastal systems. So from a management perspective, the way in which we think about stresses and manage today is often thinking about a single impact or a single cause. So we may manage for sedimentation, we may put nutrient limits on what's coming in on our rivers into our coastal environments, but we never consider the interaction of those stresses. We never consider the interaction between what happens if we increase sediments plus we add some more nutrients. What happens to a system that may have lost all its shellfish and then we add more sediments and nutrients. And it's these kinds of interactions that we need to consider to avoid these tipping points. So our current management strategies in the near shore don't really deal with this. New Zealand, like many places around the world, is seeing a massive increase in coastal development. We've got rapidly expanding coastal populations. We've got increasing pressure on the coastal environment for increasing aquaculture production, increasing the amount of shellfish we might want to harvest, and increasing use in these environments. So we need to think about how these stresses are interacting and the propensity to drive tipping points in these coastal ecosystems. And the Tipping Points project within Dynamic Seas is about addressing these points. So our challenge, within the challenge, is to think about the impacts of these multiple stresses and cumulative effects. We need to think about what that means in terms of the resilience, ecosystem function, and how that generates tipping points. And then, of course, working through our colleagues in the social sciences and in the management sciences, think about the implications for what that means in terms of a management strategy. So I just want to give you some insight today about what projects have been conducted within the Dynamic Seas. So we've got insights from historical data. We're going to talk a little bit about some experiments in the real world, a little bit of modelling, and then that fourth point there is something that we're going to be getting into in a year or so's time once we've hopefully ticked off those first three. So insights from data and theory around tipping points revolves around a lot of this change that we see in ecological indicators before a system switches into an alternate state. And what we tend to see is an increase in variance or variability in our measured response variables. So there's a lot of jumping around, a lot of noise as a precursor for falling off that cliff and into this alternate state. The evidence of this in the real world is rather little, but there has been some published work done here in New Zealand. So what we want to try and do is move from this theory, is there evidence within the existing New Zealand data sets of tipping points having already occurred within these systems? Judy Hewitt at NIWA and the University of Auckland is leading this analysis of historical data sets. So she's going in and mining regional council data sets, she's pulling together data that have got a lot of spatial coverage or a lot of temporal coverage, and she's interrogating that data for evidence of tipping points. She's isolated the criteria for the data for data suitability, and she's identified up to about 20 data sets to date. This is one example that looks at subtidal and intertidal rocky shore surveys that she's using. Now the interesting thing about this data is a lot of it is not collected at a high enough frequency or looking at the right things to actually detect tipping points within the system. So our monitoring that we're currently doing may not predispose our ability, may not allow us to detect these tipping points. We're going outside in this program. We're collecting empirical data and conducting experimental research to investigate tipping points and the consequences of them on New Zealand ecosystems. We're addressing two of the major stresses to our nearshore environment, and these stresses were identified multiple times during stakeholder workshops when we asked the community what they thought we should be looking at. Sedimentation. New Zealand's really good at delivering lots of sediments to the coast. We heard a good talk this morning about how much sediment was generated in the Kaikoura earthquake and the fact that most of that's being bulldozed into the near shore to build roads. I was heartbroken about that. I understand the need for roads. The other major stressor, of course, is an increasing agricultural production and an intensification of agriculture. That's delivering nutrients into our nearshore environment as well. So our focus with our empirical studies is understanding the interaction of those two stresses. Through David Shield and Nick at University of Canterbury and Nick Shears up at Auckland, we're looking at the impacts of increasing turbidity or sediments on the structure and functioning of our rocky reef ecosystems. Under high sediment loads, we get a shift from the dominant kelp or habitat forming species that we see here lower down to one dominated by coralline and turf forming species. Associated with that shift in the community composition is a large decrease in productivity. So David and Nick, as part of their research, is looking at how the spectral light quality changes with increasing sedimentation, what are the impacts on the production of these reef communities, and at what levels do we see a shift or a tipping point from one reef-dominated community into another type. We've done a lot of work over the years on sedimentation in estuaries and the impacts that it has on the ecosystem functioning of these systems. We know, for example, the hidden garden within these estuaries, these are the small plants that exist within the sediments that are microscopic, drive most of the production in our coastal zone. They're the key link to the organisms in the sediment, the shellfish, the worms that the snapper feed on. We know when we increase the turbidity in these systems, the lights go out and this hidden garden can no longer be as productive. We know that when the lights go out and this hidden garden isn't trapping the nutrients in the sediment, they come up into the water column and that can fuel macroalgal growth and nuisance blooms. So with this increasing turbidity, we're seeing big shifts in how these sediments function, and that will translate to shifts elsewhere in the ecosystem. We also know as we muddy the water, we begin to affect the biodiversity in those sediments. We alter the numbers of worms, we alter the composition of species that are there, and that has implications for how these sediments process nutrients. We also know from our studies, previous studies, that these sediments play a crucial role in the coastal ecosystem. It's the only way, the processes that are occurring in those sediments are the only way that we can get rid of excess nitrogen within the system. There's a process called denitrification that occurs where the specialised biogeochemical conditions, the presence or absence of oxygen, drive bacterial pathways that allow a certain fraction of that nitrogen that comes in off the land to be converted into nitrogen gas which plants can't use. So it's a natural built-in resilience around, 1 minute, gosh, I'm going to have to go fast, don't I, around these things. So the animals within these sediments play an absolutely crucial role. As we stress these systems, they begin to drop out of the system, and that ability to process nutrients, that resilience, begins to be eroded. So we're conducting experiments looking at the interactive effects of turbidity and nutrients. This is the first national experiment, the largest experiment globally of its kind actually, where we're working across 15 estuaries across Aotearoa from Northland to Southland, and we're looking at the combined effects of nutrients and sediments and how that impacts upon ecosystem function. We're going to test how these two stresses interact to affect these really important interaction networks that process nutrients in the coastal zone. And from these results, hopefully we'll be in a better place to start thinking about limit setting from terrestrial inputs into the nearshore environment. We've also got a system of modelers working on these systems, looking at trying to parameterize these complex feedbacks between light, turbidity and nutrients in the animals and plants and bacteria that process these nutrients. These models we're going to be using to go out to communities and stakeholders to talk about how these complex interactions interact and how relatively small changes within these systems can generate large changes in responses, and going to be a very useful tool for talking to communities and talking to other people within the challenge. So I guess just to summarise up before I get taken off, we're talking about, and this is the whole part of this ecosystem-based management, is that if we are going to think about tipping points, they're real, they occur in ecosystems. If we are going to move from sitting down here and looking back up and go, gosh, I never saw that coming, we're going to need to have a think about a phase shift in management, structure and governance within Aotearoa. If we want to move to forward-looking, where we can see things happening, where we can maintain these systems in a healthy way, we're going to have to acknowledge that tipping points can occur. We're going to need to start gathering data on ecosystem dynamics, look for warning signs, pay particular attention to ecosystem responses, and have integrative risk assessment of accumulative effects. We can't continue to manage individual stresses in isolation. And we need to manage to improve resilience, to restore some of these ecosystems. And of course, integrative science, society and governance is all part of that process, which links us back to the talks that we've heard earlier today. So dynamic seas are sitting down here in the bottom. Part of the results that we're generating, the conversations that we're having with our colleagues in the social sciences and in other parts of the challenge will hopefully see this science come through and hopefully shift or begin to New Zealand moving towards a more holistic and Maori world view of how to manage our ecosystems. Thanks very much.